very short. Okay, TD is further very short. Very short in the sense how will you say it is very short? Very short in the as compared to its natural time period Tn. Okay, then you can approximate this also as an impulse, just a single impulse, and you can find out the approximate expression for the response. That we will see after some time. Okay, but let us analyze this. Okay, so as you can see, so this is the equation of motion. Okay, so and these are the forces. So it is the P naught will be the force when T is less than equal to Td, and if it is T greater than Td, there is no forces acting on it. Okay, so there are two parts that interest us. So one is the force vibration part, and another is the free vibration part. So that means what I am trying to say is that means still the force is there. Okay, during that phase. Okay, what is the response? And when the force vanishes, so it will start oscillating. Still it will start. It will continue to oscillate, and that oscillation is due to the that initial condition. Basically, it is imparting at time t equal to dt. Okay, so that part, that is the force regime and the free regime. That we two regime we want to discuss. And remember that the system is an initial condition at the start. Okay. So force vibration phase that we already discussed, it very simple. So we know it is like a ramp step force. Okay, but it's finishing at time t equal to td. So for t less than equal to td, so I can very much easily write that xt equals to delta st 1 minus cosine 2 pi t by t. Okay, is it clear? That you have already done, right? You can go back to your notes or PPT and you can see this is the response for undamped system substitute a step loading. But here it is that the step load is finishes TD, time TD. So we are concentrating on this time till TD. Okay. So let us first discuss about this thing. Let us try to plot the DLF, that is the dynamic load factor, versus Tn by Td. Okay. So what is there? So I can write this thing as so xt by delta st is equals to 2 1 minus cos 2 theta, right? So 2 sine square pi t by tn, right? So what I have got, sorry. So xt, so this is the forced regime. Okay, forced regime. Xt by delta st is equal to 2 sine square. So please see it carefully, okay? Because you see there are some plots are there, okay, that I am going to discuss now. So if you, without attending classes, without understanding, if you go through the plot or read the book, it will be very confusing for you, okay? So at the first time, understanding the thing will be quite difficult for you, okay? So 2 sine square by, sorry, what I have written wrongly, Tn, right? Is Tn, okay? Right, correct? For, remember that this is for T less than equal to Td, correct? T less than equal to Td. Td, anytime T, this is Pt. Okay, so now tell me, so my DLF is what? DLF is the xt max divided by delta st. Okay. So now you see, so T cannot be more than Td, right? So because we are concentrating on this part only, okay. So actually very much I can put it here Td, okay, and see the lower values of Td, right? For lower values of Td. Or you can intuitively say that if my T by Td is less than equal to half, right? So first consider this part, okay, less than half. So if T by Td can Td by Tn equals to half, then what will happen? So if I substitute here for any time, okay. So tell me what will be my DLF. Tell me what will be my DLF. If Td by Tn is, let's say, at half, so what will be my DLF? The first half, and then talk about the less than half. So if Td by Tn is less than half, that means that is the duration of the pulse is less than half of the time period of the system, natural time period of the system. Then what would be my DLF? That is, DLF is nothing but xt max by delta st. For xt by delta st, I have written here. Tell me. So first tell me, if Td by Tn is half, then what will be this ratio or DLF? Tell me.
So 2.
So it is, if it is Td by Tn is half, then it is 2. If it is less than half, then will there be any time where it will be, it will be 2 or more than 2 or less than 2 always? Remember that T cannot be greater than Td, okay? So if Td by Tn is less than half, okay, so what will be my DLF? Less than 2, always less than 2, right?
Yes, sir.
Yes, correct. Less than 2. So, less than. So, if let's say I am going to plot TD by TN versus DLF for force regime, remember force regime, okay. So, it will be, let's say this is half, 0.5, and it's a 1, 1.52 or whatever. So, it will be something like this, right? And for all TD by TN, okay, I mean, half it is 1, right? I'm sorry, half it is 2, the ratio is 2. And if you go more than that also, I can say it is the maximum. I mean, peak DLF is 2, right? Because the XT max can take the value of, XT max by delta ST can take the value of 2. So, is this plot is correct to you? 1, 1.5, 2, right? So, if I just want to plot DLF versus TT by TN, okay, so can I plot this? Force regime or whatever. Is it okay? This value is 2 obviously. Okay. This plot is clear, right? Or any issue is here still? You just told, right? If TT by TN is less than half, then it is less than 2. Okay, so TT by less than half, it is less than 2. And usually it is starting from 0, right? If TT by TT is 0, then it is sine 0, so it is 0, right? 0. Clear? So this plot is clear. So then move to the free racing. So free racing, what will happen? So at the end of the time TD, so there will be initial displacement. So there will be, that is at xTD basically. So xTD will be P naught by K 1 minus cosine omega n TD, and you differentiate it and then substitute there. So you will get the x dot TD. So that is the velocity at the time at the end of the pulse. Okay. So that will be nothing but P naught by K. What will happen? Omega n sine omega n TD. Correct? So that is at the end of this rectangular pulse. That is at time t equal to dt. I'll get this as initial displacement and this as an initial velocity. And you see after tt there is no force. Okay, so it will just oscillate due to this initial displacement and velocity. I can very easily write what is my response. So during the free regime, okay, remember that force regime we have already done and we have plotted this DLA versus TT by TN. No question about that. Okay. Now over this plot, I'll plot the I'll just superimpose the what is called for the free regime. Okay. So xt is equals to xtd, right? It will be cosine omega n since it's starting from td time t minus td plus x dot td divided by omega n cosine omega n t minus t. That is very simple, straightforward. Okay. So this actually can be written as, so what is the amplitude actually? Basically we are interested in amplitude, right? So amplitude will be xtd whole square plus this type of thing you have already done, right? xtd by omega n square something, cosine of something not interested. We are interested in this amplitude. So what is this amplitude? The substitute xtd and x dot tt here and tell me what you are getting here. xtd and I have just written what is xtd and x dot tt. Correct? This is nothing but the displacement and velocity, okay, of that single degree of freedom system at the end of the pulse, rectangular pulse. Substitute here and tell me what you are getting. So that will be basically x max actually, okay, xt max. So we are amplitude here considering. Okay. What you got? Very quick. You are understanding, right? So this is due to the initial displacement and initial velocity. This is the response of a system. Okay, because at time td after t equal to t greater than tt, there is no pulses, no force is there. So it is just due to the due to this initial displacement velocity, it will undergoing phi vibration. Okay, so and the phi vibration response is this. Now I am going to substitute this and this that I already obtained, and I am writing in this format. A cos something, right? You know, e cos omega n t minus t or something format. So this is not interest to me, so I want to know what is the amplitude. Right? So what is the amplitude? Tell me quickly. What is X max? Or tell me what difficulty when facing or when finding this. You can tell whatever way. Either you tell the answer or tell me, sir, I am facing this difficulty, I am not able to understand. Tell me. You have to reply.
So 2 P naught by K cos omega and T d by 2.
2 delta st p naught by k delta st into
Cos omega and T d by 2.
cos
Omega and T d by 2.
So everybody getting this? Any other people? Please confirm.
So sorry, sir. So that is sine omega and T d by 2. Sir.
Please confirm someone else. Because square is there, so you should put mod actually, because you are interested in the mod value. So everybody getting this value, anybody has any difficulty in getting this value, please speak out. Unless you speak out, I am not able to understand whether you are understanding or not. Okay. So please speak out if you have any difficulties.
Same, sir.
No problem. So everybody got this. So I can write this as so now DLF is X max by delta st. There is 2 mod of shine. Now I'll write in terms of the TD by Tn, right? So omega n equal to pi by Tn. So I can write 2 get cancel out. So pi TD by Tn. Okay. Now I'm going to plot this. So let me write in the next slide again the same thing. So 2 sin pi dt by Tn. Okay. DLF, this is free regime. Okay. DLF equal to 2 sin pi Td by Tn. Free regime. Okay. So free regime, T can take any value, right? Greater than Td, any value it can take. Greater than Td, any value greater than Td. No problem as such. So now T by Td by the DLF. So now tell me if Td by Tn, Td by Tn is Td by Tn. Td by Tn 0. What is DLF? Td by Tn 0.5. What is DLF? So tell me quickly the DLF values. Td by Tn 1. What is DLF? Td by Tn 1.5. What is DLF? Td by Tn 2. What is DLF? Tell me. First DLF.
0.
Second.
2.
Huh?
2.
Second. Third.
0.
Fourth.
2.
Then
0.
0. 0.5, 1, 1.5, 2, 2.1, something like that. Okay. So what is happening? 0.5 it is 2 here. So let's say this is the 2 line. 1, 0, 1.5 it is 2, then 2.2. Here it is 0.5, how much? 2, right? So it is something like this. Sinusoidal. Am I right? It's 2. Are you agree with me? DLA versus TD by TL. Clear?
Yes, sir.
Okay. If it is clear, so then just see this figure. Okay. So you'll find this figure in the book. Okay. So you see all those explanations will not be available, and you see the books for the first time without attending the classes. Believe me, it will be very difficult to understand. First time you will see this figure, what is going on, why 2 plot in one figure, what is really confusing actually. So, but if you think about this way, separately 2, and then you will find out that this is nothing. Okay. So then this is the force response that we plot and the free response. So in a single plot we are showing. Okay. Because you see our aim is to find out what is the DLF, right? For TD by Tn value. Because the ultimate goal is that given a, let's say, pulse. Okay, some pulse we have given with some TT. So we just go to the plot of actually this plot. So this is the overall maximum because the envelope, right? Envelope. Okay. So envelope till here, we see till 0.5. Which one is larger?
So force response is larger than free response.
Free response or force response? Which one? Till here.
Force here.
Both are equal.
What?
Both are
Equal.
equal there.
Equal.
No. I mean, in this range.
The force.
Which one? Force is dash dash. So is my eye got bad or is the force is here lower, right? Free is, I think, dash dot is more. Which one is more? Or you are not able to see the figure properly?
Yes, sir,
So
in that
free
area.
response. So free response is more, sir.
Yes, so free, if it is TD by Tn is less than half, so it is the free response. Okay, that is governing. Okay, so here the overall maximums are plotted here. So actually our aim will be, so TD by Tn will be given. So from this diagram I will just pick out the DLF value, and once we got the DLF value, we will multiply with the what? The delta st to get the maximum displacement. Okay, and from that maximum displacement actually we can find out, so maximum displacement, right? Maximum displacement multiplied by the stiffness will get the equivalent static force, because you see the designer not interested in this, what you are doing, pulse load, these things that they in the office, there is just some graph is there in the code or in some provision. They'll go to the graph, find out TT by, okay, TT by Tn is this, so I will get the DLF multiplied by the static displacement, so I'll get the xt max, and so from xt max I can find out the what is called the equivalent static force, because in the design, even earthquake also, okay, the earthquake code that is available, so there are the preliminary design step is the by based on the equivalent static load. Okay, so you are basically finding a some amplified, or I mean, what should I say, I mean, some factored static load. Okay, in addition to the normal static analysis load that you consider. Okay, so and once you got the then basically the load will get increased, and based on that load you can find out what is the shear force bending moment in the system, and then you can design accordingly, right? So that is the aim, okay, to finding out this. Okay, so this type of plot, so this DLA versus TT by Tn is called the shock spectra. Okay, so as I told earlier, so it is coming from the response spectra actually. So response spectrum is nothing but the uh, I mean the maximum value of some quantity, so that quantity can be displacement, velocity, acceleration in the y-axis, and in the x-axis it is the time period of the system. So for this pulse type of loading, since the pulse duration is important, so in the x-axis it is TD by Tn versus the DLF. So DLF is nothing but a kind of maximum displacement plot right here. Okay, so this type of plot, this type of response spectrum, so it is a kind of response spectra which is called the shock spectrum. Okay, so similar shock spectra can be obtained from some other types of loading. Okay. Okay. So as I told, just the same thing it is written here. The plot showing maximum deformation of a single degree. Yes, remember that single degree of freedom system as a function of the natural period Tn of the system is called the response spectrum. When the excitation is a single pulse, so in this case it is calling as the shock spectrum. So how to use shock spectra? So the given data Tn is given to you, right? Structure, natural, time period, and pulse amplitude is given. Okay, so that the pulse duration you can find out. So from that, from the DLA plot, you can, I mean DLA from the shock spectra, you will get the DLF value, right? Obtain DLF corresponding to that TD by Tn from the spectrum. Okay, then you can find out the maximum deformation, that is nothing but xt max equals to delta S into DLF, that is P naught by K into DLF. Very simple. So once you got the maximum deformation, you can find out the equivalent static force. What is that? Equivalent static force Fs max, that is equals to K into x max. Okay, that is P naught into DLF. Okay. So then once you got the equivalent static force, okay, then you can find out the internal forces. What are the internal forces? Like shear force, bending moment, and then you can bending stress, shear stress, whatever that you already expert of it, right? Solid mechanics or your basic structure analysis. Okay. So similar type of shock spectra can be obtained for other pulse excitation like this. You see, this is for the half sine pulse. Okay. Again, similar type of plot, force response, free response plot, and this is the overall maximum. Okay. This is for the triangular pulse. Okay. Now, so far we have ignored the damping, right? So experimentally also it has been observed that so this type of pulse type loading, which is only for very small duration. So this is one of the experiment is done, and this is the result. Okay, for the DLF versus TT by TN for damping, including the damping. So you can see here, right, that the effect of damping is very not that much as opposed to the harmonic excitation, where you have, remember, you plot the dynamic magnification factor versus frequency ratio, right? R, right? That is omega by omega n versus the magnification factor. So they are at or near the resonance. The damping has a very important effect, right? Okay. So without damping, so it is actually unbounded type response, right? Okay. So but here it is, you see, it is for the structural system for which the damping ratio will usually find out 10 less than 10%. Okay, so it is not that much, and also will be a little bit on the conservative side, which is good enough. Okay, not too much conservative, but I mean little bit on the conservative side in the design, so it is good enough. So you can just read that slide. Okay, then we'll go to the next thing. So that is the difference with the harmonically excited this thing, the second point. This is in contrast with the results of a harmonically excited force vibration case, where damping is very important on the maximum steady state response at or near the resonance, especially at or near the resonance. So cumulative energy distributed in many vibration cycle prior to attainment of steady state is substantial. Okay. But here it is not the case. So here conservative but not overly conservative estimate of the response of many practical structure with damping. Obviously practical structure there is damping. So what we are ignoring is not actually correct. But it is saying that it's conservative but not overly conservative estimate. Okay. So that you can do for pulse excitation. So maybe obtained by neglecting the damping. That you can do some conservative but not overly conservative estimate of the response. For many practical structure you can obtain by neglecting the damping, although it has damping. Okay. For this, what excitation? Pulse excitation. Okay. Now I will ask one thing. Okay. So I hope this part you are agree, right? This side you are agree, because I have shown two plot, right? So one is this plot. So this is for the free regime, and this is for the force regime, the dot line or whatever. Okay. So for this, just tell me why this dot line is lower in the dash dot line. Okay. I mean in this part, or it is just arbitrarily plotted or what? Yes. Look at the DLF expression and tell me. For the both the thing, that is the, so I'm giving you the hints. Look at the expression for the force response and the free response DLF for TD by TL less than half. Okay. Why the force response one is below the free response one for that zone? Yes. Look at the two DLF expression. Okay, so for your convenience, I'll show here what is the DLF expression I have. So the free regime, it is 2 mod of sine pi TD by Tn. Okay, just note it down. This is in the free regime. Okay, and force regime is where it is gone. Force regime, it is the 2 sine square pi TT by Tn. Okay. Now you can tell me, right? It's simple.
Because that 2 sine square curve is having its values more greater than that in that area. Because 2 sine square we can also write 1 minus cos 2 theta, and we can compare the values also.
Yeah, comparing the value, and a sine square, in one case it is sine square, it is some only sine, the square will be lower, right, if dt by t is less than half, right? Let's say sine 30 degree, what is sine 30?
1 by 2.
1 by, so if I take square 1 by 4, so which one is more, 1 by 2 or 1 by 4?
1 by 2.
Right. So in that case, so that's why free vibration phase is more, you see. Okay, got it or not? Because you are considering only this part, not you are going beyond this. So T by T less than half. So that means sin pi by 2 or less, right? Half. Sin pi by 2 or less. For sin pi by 2 or less, so if I take the square of this, thing, let's say sin pi by 6, right? So pi by 6. So sin square pi by 6 more or sin pi by 6 more? So based on that, here the two plots are different. Okay. Now it is clear, I hope. Okay. Okay. Now, so we'll just quickly discuss about the last part and then we'll move to a problem. Okay, based on this, what we are now going to discuss. Okay. Approximate analysis of short pulse. So now it is saying that if Tt by Tn is very less than 1, okay, very short. That is the duration of the pulse is much shorter than the time period, system natural time period, or strictly speaking, Tt by Tn, if it is less than 1/4, actually 1/4. Okay. So then you can treat that impulse as just a pure impulse. Okay, pure impulse of what magnitude? That Pt, right? So Pt equals to, we know, 0 to Td. What is that? P naught, or what is Ptd, right? Ptdt, I think. Sorry, this should be I, impulse magnitude, right? I is equal to Ptdt. Correct? That is the impulse, magnitude of the impulse. Right? So area under the basically, whatever. Okay, because you see there will not be an exactly triangular type or those type, those are idealization. So let's say very short pulse of something arbitrary like this, arbitrary, but very short duration. Okay, so then I can find out the impulse, right? That is the area under this thing. Okay, so that is the impulse. So and I can consider that pulse loading as a pure impulse loading. Now tell me, so what is the response due to the impulse of magnitude I? So response due to impulse of magnitude I. What is that response? Just a single impulse, single pure impulse. That's all. If Tt by Tn is less than 1, this condition is 0.25, less than 0.25. So then what is xt? Tell me. So I have given you the impulse magnitude I. What is the response? Come on. Forget.
The 1 by m omega and integral of 0 to t I sin omega and t minus tau d.
Where is the integral coming into the picture? It's a single pulse. If there are many pulses, then I will integrate it. So it is just I by m omega n sin omega n t, right? Here, any doubt with this expression? Please speak out. Anybody has any doubt? Let's go to the presentation, the structural dynamics underscore 4.1. So there we discuss, right, the response due to unit impulse response. So that is the response due to impulse of magnitude unity. That is what? 1 by, for undamped system, 1 by m omega n sin omega n, something t minus tau if it is shifted by tau. If it is not shifted, then it is sin omega n t for undamped system. So this is the unit impulse response. So already discussed at the beginning of this chapter. I mean, that is the due to arbitrary loading or general forcing function. Okay, so unit impulse response. So this is due to unit value of the impulse. Now for if the magnitude of the impulse is I, then it will just multiply, and it's a single impulse, right? Single impulse. And if there are some many such impulses, then you have to integrate it. Clear? Okay, if it is clear. So now tell me then what is xt max? Quick. What is xt max?
So I by m omega n.
Correct. I by m. So if I write in terms of Tn, what is the expression? Tell me.
So it I into 2 pi by k into Tn.
I into 2 pi by k into
Tn. Normal.
I Tn or in multiply Tn what?
So what?
I into 2 pi by k into 1 by Tn or Tn?
Yes, sir, 1 by Tn.
1 by Tn. Okay. Correct. So you see, I can write, so you will see the response, maximum response is proportional to the impulse, because this k, Tn or m omega is a fixed for the system, right? Proportional to the impulse. Okay, so let us find out. So for what? Let's say rectangular pulse. But remember that there is very short duration, okay? Td. So I am writing the condition is that this is applicable only for this. Correct? So for this, tell me quickly what is my DLF? Quick, come on. Any difficulties? You have to speak out. I am again repeating. This is symmetric triangular. What is DLF? You know DLF, right? DLF is xt max divided by delta st, that is P naught by k. So for your convenience, I am writing here. Delta st equal to P naught by k. So here also same. Again, I am writing here delta st equals to P naught by k. And this you already know. So tell me what it is for this and what it is for this. You know what is I, right? What is I? I is the area under this. Area under this. What is I? Integral of pt dt. 0 to td, right? So that is the basically the magnitude of the impulse, that is the area under that impulse. And the condition is that td by tn should be less than 1. Delta st is P naught by k. This is the DLF, xt max divided by delta st. So what is for the first one?
2 pi into Td by Tn.
What is for the second one? Anybody not able to find out this value? 2 pi Td by Tn. Please speak out. Repeat and listen.
So pi Td by Tn.
Now you're finding it easy. Now do it for this. Td. Half sine pulse. What is TLF? Again I am writing xt max divided by delta st. Condition is again that Td by Tn less than 4. Okay. Now what is the formula I will write here? So xt max is equals to I by k 2 pi by Tn. I by k 2 pi by Tn. So any doubt with any expression of this approximate analysis of pulse load? Whatever we have discussed for this case, because you are going to now solve a problem, you should solve the problem, okay, by your own, okay. So please ask me if you have any doubt. So I am repeating again. So while you are calculating, I am repeating again. So what is this value? So if the pulse duration is very short in the sense as if Td equal to less than Tn by 4 or Td by Tn less than 0.25, okay. So in that case, we can consider that whether it is a rectangular pulse or triangular pulse or half sinusoidal pulse, we can consider them as just a single impulse, short impulse. Okay. So now you know already done that what is the response due to a impulse of unit magnitude, right? That is called unit impulse response function. Okay. You remember ht minus tau. Okay. That is 1 by m omega n sin omega n t minus tau. That is for undamped system. Okay. So if there is no time shift, then it will be just 1 by m omega n sin omega n t. Clear? So that is per unit magnitude of impulse. Now if my impulse magnitude is I, which is nothing but the integral of pt dt, t ranging from 0 to td, td is the duration of the pulse. Okay. So I can write it is nothing but xt equals to I multiplied by that thing. That thing means 1 by m omega n sin omega n t. So what is the maximum value of xt max? So when sin becomes 1, right? Because the sin can take the value of 1, maximum value of 1. So that you basically are getting I divided by what? M omega n. So that I can in some different form I can write I by k into 2 pi by tn, because I want to introduce the terminology tn, time period, okay, of the system. Now we know the DLF is xt max divided by P naught by k, static displacement, delta st. Right? So that is what we are going to find out. So DLF for 3 types of loading, that is rectangular pulse, symmetric triangular pulse, and half sine pulse. So 2 already done, right? So you can, so just I am show here how it is find, you are finding here. So you can say what is this for? So half it is TD into P naught, right? This is the area. So that is basically I. So then it is 2 pi by k into 1 by Tn. I'm just substituting in this expression. Okay. So I is this area under the triangle, and 2 pi by 1 by Tn. Okay. Got it? So now P naught by k is delta st. So if I go on the other side, 2 get cancelled out, you see it will be pi into Td by k. Okay. So I have shown here also. Clear? So I don't think you have any doubt. So if since you have do not have any doubt, please do this. Tell me what it is quickly. Why are you taking so much time? We have quickly done the two things. What is the problem here? Because integration comes into the picture. So you have to do integration. You have to know how to do integration. Okay. Yes. Come on. What is the value? DLF. Or at least speak out what difficulty you are facing. Otherwise, I will be silent. You will be silent. Everything will be silent. Come on, find out. This is half sine pulse area under this diagram. Okay. I think nowadays people are learning area under the curve in class 10th class or what? I learned in only 12th class, 10 plus 2. Because in 10th that time differentiation integration is not there. I think nowadays in the 10th class it can most probably.
So P naught T by 2 pi.
What is the final result? DLF, you tell me. DLF, tell me DLF. Please find out area under this curve, which will give you I. Substitute here and find out xt max by delta st. Delta st is nothing but P naught by k. And then tell me what is DLF. Again, speak out if you find facing any difficulty in finding out this DLF value for not only for this half sine pulse or for this or this. Please speak out.
Sir, I is coming to be 2 by pi P naught T naught.
Just tell me DLF. What is directly DLF?
So 4 into TD by Tn.
Okay, correct. Anybody has any difficulty in getting 4 into TD by Tn? Difficulty? No difficulty. Very good. So that is the thing, it is written here, so you can just look into that. Now we will solve one problem, okay, based on what we just learned. Please do that. So first check it whether you can apply what we just learned applicable or not. That is TD by Tn is less than 1/4 or not. That you have to see, right? If it is not, then you cannot use that approximate method. Okay. I mean, you cannot consider the load as a single impulse. So that you first check TD right here. So what is TD here? 0.08, right? Second, right? So you see how short it is, 0.08 second, not even 1 second, right? Not even not even 0.1 seconds so far. Oh, what is the sorry? What the water tank? Yeah, this is. So understood, right? What you have to do? You have to find out DLF, basically. So once you got the DLF, then you can find out the equivalent static force. DLF is really not required. I mean, you will get XT max. Right? So XT max is multiplied by K will give you the equivalent static force. So find out XT max basically. XT max. So XT max though is further simplified. Right? What is just I'll go back a little bit to see the formula. So XT max is I by m omega n, right? I by m omega. XT max. I by m omega n. Once you got a XT max, you have to find out the equivalent static force. Equivalent. EQ means not equation, right? Equivalent. Equivalent static force. So that will be equal to nothing but XT max into K, right? Stiffness. K is given here, right? This is the K. XT max equals to this. That I've just talked about, right? I by m omega. I is the impulse. That's the area under this. M is given or not? Given. Omega n is given or not? Not given, but you can find out. Omega n is equal to K by M. K is given, M is given. Okay? So you can find out A, M is there, omega n you can find out. I is nothing but the area under this pulse. Okay? Then you will get XT max. XT max multiplied by K, right? Force. Stiffness into XT, right? Damping is not participating. So equivalent static force. Once you got the equivalent static force, so it is like just cantilever, right? Cantilever with a equivalent static force acting here. So you can find out the shear force and bending moment. So what is the shear force diagram and how is the bending moment diagram? Tell me. Cantilever subjected to a tip and load. Okay. So this will obviously you know. So this will be the SFD and this will be the. So we just find out the values. This will be nothing but the maximum equivalent static force only, and it is nothing but this value will be maximum equivalent static force multiplied by this height. Okay. And then this and this also. Okay. Any doubt? I have explained everything. There should not be any doubt. So how will you find out I? Capital I? Tell me.
So we can break the entire graph into like different parts and then triangle and maybe trapezium.
That depends on why you have learned so many things. Trapezoidal, Simpson one, many things you have learned. Right? So try it. We use trapezoidal route at least, right? Use trapezoidal. Simpson one route is you see if it is applicable, then you can apply. Right. So anyway, you will find out I. Okay. Then I by omega n, XT max will get maximum deformation. Then multiplied by stiffness, lateral stiffness basically of that column or the tower, okay, of the water tank. Then you will get the equivalent static force, and then you can find out that. So it is like a cantilever subject to a tip load. What is the tip load? Equivalent static force. So from that you can find out shear force and bending moment diagram. Once you got the shear force and bending moment diagram, you can find out the internal stresses. Clear?
So I is coming to be 5.34.
That I do not know. Tell me the final answer. I know CFSFDBMD. Maybe correct. Yeah, 5 point something. I yesterday solved it. Yes. What is the shear force value and what is the maximum bending moment value? Come on, you already got I, right? Someone got I think. So just divided by m omega n. M is given there, omega n you already obtained. And equivalent static force is just multiplied by K. That's all.
X naught is coming to be 0.02.
X naught. XT max, right?
Yes.
Okay.
Sir, I'm
Then
getting shear force as 28.72 kilonewtons.
shear force as
28.72 kilonewton.
okay. Maybe some numerical calculation problem. So
I'm
what I
getting 30.01.
I got 30.05. Let's see how much here. 30.04. What bending moment?
Sir, 731.68.
Okay. It's okay, fine. Okay. So those who are not able to do it, please tell me if you have any difficulty. Try to do it in few minutes. Okay. Okay. So I continue with the normal classes today because as mentioned by CR yesterday that not many people has doubt. So we'll conduct our quiz on 8th, right? Wednesday. Wednesday time. 8th. Yeah. It's from 12:30 and the duration of the exam that is maybe 35 to 40 minutes. Okay. So you see the questions will be very simple. Okay. And it will not take much time to calculate except the one problem that is giving a 4-number problem. So that just some calculation is there. Okay. And I'm giving you hints also. That's that type of problem we have done in the class. That's all. So that will be just time consuming. Others are very simple, but you think about that first. Read the question carefully, okay? And instead of asking someone else and doing some what is called unfair means, try to think about yourself. And it is very simple question. And I am expecting that most of you will get above 10 at least, okay, out of 15. What is this? Okay. So anybody facing any difficulty by solving this problem? But yeah, so what is the value of TD by TN here? Is it less than 0.25 or not?
Yes, sir, less than 2.
Less than 1/4, right? 1/4. Okay, fine. So in 15 class we have finished single degree of freedom system, and that is actually we are going on the right track. So it should take 20 classes to finish single degree of freedom system. So 5 classes, why less? Because 3 classes you should take for a generalized single degree of freedom system, which is not in your syllabus, fortunately or unfortunately. So 18, and then 2 classes that I kept aside for the numerical method. Okay, solving numerically like central difference method, Newmark's method. So at least we'll discuss about this 2 methods. Okay. And please try to see some responses due to harmonic load. I already mentioned, and someone also shows interest that we'll be able to do using Rangikutta or whatever. So try to solve it using different, some numerical method, whatever you have learned. I hope you have learned central difference method or something like that. So try to solve the second order differential equation, single degree of freedom system, subjected to a harmonic load, a sign quotient. And then there is a closed form expression available, right? That is available in the books or PPT or whatever. So you just see that, try to plot it and compare the results. So that is for your understanding and convenience. Okay. And see whether it is matching or how much difference it is, and try to see. And you can play around it by changing the frequency, natural frequency, by changing the excitation frequency, by changing the amplitude of the excitation, or anything else. And damping ratio, most importantly, damping ratio you can change and see what effect it is giving. Okay. So just make you can make, you can do it in Excel, or for the numeric method you can take the help of the MATLAB. So that will be a little bit learning for coding also for you. Okay. Okay, so I'll stop it here. If you have any doubt, you can ask me. I'll be here for 2 more minutes. Okay. Or otherwise, if you don't have any doubt, you can leave. No problem.